Swayam Prabha. Digital India. Educated India.
Hello everyone. So, we will discuss now the forces on ring and traveler. So, we have discussed earlier the forces acting on the yarn and traveler also. Now, further we will discuss on this issue. The power provided by winding tension in the spinning system is expended by means of the following ways. So, whatever power we are in the winding tension provides to overcome the ring traveler friction, to overcome yarn traveler friction. So, one is the ring traveler friction is there, then yarn and traveler friction is there, to overcome the resistance of the air to the rotation of the loop of yarn between the thread guide and the traveler, that is the yarn balloon, air drag force, the portion of yarn between the traveler and the package, so there are different types of forces are there and the power provided by the winding tension has to overcome all this. So, first is the friction between the ring and traveler, friction between yarn and traveler, and the air drag in the balloon zone, and also air drag at the between the traveler and the package. So, there is also air drag. Now, assuming that the traveler contacts the ring at only one point, okay, and the condition for the equilibriums are balancing the horizontal or radial components. This is the, we have to balance the horizontal component first. Now, if we try to balance it, this is the different component of forces acting on the traveler. Now, in the radial or horizontal component, when we try to balance, so it comes out to be the C equal to Tu cos alpha plus S cos gamma minus Tt cos epsilon 1. Now, try to see here where C is m r omega square. The centrifugal force required to keep the traveler rotating is that r dash equal to radius of the rotation of the CG of the traveler. So, that is r dash S is the normal reaction between ring and traveler. So, that is the S is the normal reaction between ring and traveler, here is the traveler normal reaction. Okay. And r dash is radius of the CG of the traveler, Tt, this Tt is the tension in the yarn at the traveler in the balloon. So, this is the Tt, tension in the yarn at the traveler, that is the balloon tension you can see, and Tu is the tension in the yarn between traveler and balloon. So, Tu is that here Tu traveler and bobbin. So, that is the yarn tension. So, here you can see C is the centripetal force, the Tu cos alpha, tu cos alpha at this direction and s cos gamma, s cos gamma. So, this is acting in this direction. Okay. Though both the component and T t, this is on the other direction, minus T t cos epsilon 1 outer side, okay, and centripetal force, okay. C is the centripetal force, that means C, this C is moving outside. So, two components are inside inner direction and outer direction, two more components. So, C is dependent on the m r dash omega square, that is the mass of the traveller. Now, balancing the tangential component, this is the normal component balancing the horizontal component, the radial component. Now, we are balancing the tangential component. So, tangential component if we try to balance, this will be the mu s plus T t cos, the T t is the this force and cos epsilon 2 will act in this direction equal to T u, T u is this force, T u sin alpha. So, this is the, and sin alpha will be in this direction. So, T u cos alpha in radial direction, sin alpha will be in the tangential direction, where mu is the coefficient of friction, mu s will act. Now, balancing the vertical component. So, we have seen the radial component, tangential component. Now, we are trying to balance the vertical component. Vertical component is that T t third direction, it is a cos epsilon 3 is the vertically it is working. So, T t has got 3 components, epsilon 1, epsilon 2 and epsilon 3, which is vertical component, and S sin gamma. So, S has got also 3 components, S sin gamma, this is S is there, and sin gamma will be working vertically downward. So, S sin gamma and multiplied by plus m g. So, these are moving downward, these two, and T t cos epsilon 3 is moving upward, vertically upward. So, there are 3 different directions. Now, where mg is the weight of the traveller, here mg is the weight of traveller. Now, we can derive T t equal to, this is T t, T t is nothing but T u E phi mu 1, okay. Phi is the angle of lap of the yarn with the traveller, angle of wrap of yarn around the traveller. Mu 1 is the coefficient of friction between yarn and traveller. Okay. So, these are the conditions here. Now, from this equation number 4, what we can get here, T t equal to A T u. So, T t equal to A T u, where A is the e to the power phi mu 1. So, that is replaced here. and using equation 2 and 5 we get. So, this is equation 2 and equation 5. So, we replace this T t in equation 2, what we get? We get the S equal to T t sin alpha minus A cos alpha by A mu. So, that from the equation 2 we get equation 6 using the equation 5. Rearranging equation 1 and using equation 5 we get. So, equation 1 is this and equation 5 we got T t A T u, and after rearranging what we get? C equal to T t by A. So, T t by A, T u equal to T t by A. So, from there T u equal to T t by A. So, we are replacing T t by A, then cos alpha minus A cos epsilon 1 equal to S cos gamma. So, if we just replace this T t here, we will get here. Okay. So, and substituting S from equation 6. What is equation 6? This is equation 6. So, here this S value, S we can substitute here in this equation. What we get? We get this value. So, A is S is substituted here. This is the S value we are substituting in equation, in this equation. Okay. So, we get the C value, and this C value, rearranging this, what we get? We get the T t value in this form, which is A mu C divided by sin alpha cos gamma plus mu cos alpha minus A multiplied by mu cos epsilon 1 plus cos gamma cos epsilon 2. So, from the 3 directions of forces we can get T t value, and T t in from the equation 3, which is T t cos epsilon 3 equal to sin S sin gamma plus m g. So, we get this value, that is by rearranging the equation 3, sin gamma is equal to T t cos epsilon 3 minus m g by S. This S is coming to the denominator. So, this sin gamma we can use substituting S from equation 6. So, this is equation, what is equation 6? This is the equation 6. This we are substituting here S. So, we get sin gamma equal to A, this is the S value. So, A mu is coming to the numerator. So, A mu T t cos epsilon 3 minus m g divided by T t in sin alpha minus A cos epsilon 2. So, just by rearranging we are getting sin gamma, and m g is small as compared to the tension of the yarn. So, it can be neglected with respect to T t cos epsilon 3. So, epsilon 3 is also small in practical sense. So, here the epsilon 3, this angle, because it is a vertical deflection at any point, it is small. So, the cos epsilon 3 we can assume as 1. So, at this stage no air drag is there. So, hence the epsilon 2, this epsilon 2 will be 90 degree. So, cos epsilon 2 will be 0. So, with no air drag. So, when air drag is there, there will be some inclination. In that case, the epsilon will have some lower value, otherwise it is 90 degree. So, epsilon 1 is also close to 90 degree, which makes cos epsilon 1 close to 0. So, epsilon 1 also 90 degree, epsilon 2 is also 90 degree. Hence, a mu cos epsilon 1 can be neglected. So, that will become 0. Therefore, the equation 8 which we have got, this is the equation 8 we have got, that is it becomes very simplified, it is close to approximately a mu by sin alpha. So, that T t is approximately a mu c by sin alpha cos gamma plus mu cos alpha, okay, where epsilon 2 and epsilon 3 are almost 90 degree. The epsilon 2 is 2 and 1 are 90 degree and epsilon 1 is almost 0, it can neglect. So, this equation is simplified and C equal to m r dash omega square. So, we can use this one. So, T t we get T 0 minus this we have derived earlier, T 0 minus half m r square omega square. Therefore, T 0 we can get m a mu m r omega square, okay, and sin alpha cos gamma plus mu cos alpha plus this one. So, T 0 will be T t plus half m r square omega square. So, T t we have got. So, T 0 we can calculate here from this. Sin alpha sin gamma cannot be greater than 1 in equation 8 for any value of a mu. So, there is a minimum value of alpha below which the traveller will not continue to run. Most likely the value is of a is 1, mu equal to 0.5. So, that the limiting value of alpha is sin inverse alpha, that is sin inverse 0.5, that is approximately 30 degree. Practical value of a mu is 0.2, hence alpha is rarely less than 25 degree. So, alpha is more than 25 degree. So, T t by C equal to a mu sin alpha cos gamma plus mu cos alpha, that we have already derived. So, from here we can see the T t by C is changes with the alpha. How it is changing? For different mu and A combination. So, for different mu and A combination we can see that T t by C is decreasing sharply, then it is flattened, and at later stage it is at with the higher angle it is increasing. So, alpha is always typically more than 25 degree. If the ion is assumed to be weightless, no air drag is there, and if ion axis velocity, axial velocity is neglected, so then the ion would be of straight line. So, tangential component of the ion tension is constant from the traveler to the package. In practice, the effect of weight of ion, air drag and the velocity of the ion along the length have to be considered. So, here you can see this is the angle 0 COP radius, and this is ring radius, is the ring radius. The centripetal force is required on each element of ion to keep the ion rotating. So, T equal to some constant minus half m r square omega square centripetal force, here is the r. So, since T equal to T u, when r is capital R, ring diameter equal to bobbin diameter, and T equal to T w when r is r 1. That means, T w will be T u plus half m omega square r square minus r square. So, that we can get from this relationship. So, tension in the ion keeps increasing as it moves towards the package. Okay. The shape of the ion path. So, the tension increases from the towards the package, okay, from the ring, from the ring side traveler. The shape of the ion path will be such that the movement about the axis of the tangential component of the tension must be constant, since the air drag is not considered here. Okay. So, when air drag is considered, to overcome the effect of air drag, there must be a net tangential force on each element in the direction of the rotation. Okay. The movement of the tangential component of tension increases from the traveler to the package, and that is how this is the effect of air drag here. So, R 1 T w is more than R T u sin alpha 0, and here R 1 T w equal to R T u sin alpha 0. So, that is how it is happening. The kinetic energy, so axial velocity is considered, the kinetic energy of rotation of each element of ion is decreased as the ion goes from radius 1 to r 1 r to r 1. The moment of tangential component about the axis must decrease from traveler to the package. So, that is there. So, what we have now discussed here, just we have to try to understand the ion tension at different conditions. So, in the next session we will discuss one new topic. Till then, thank you.